All right, so welcome back. In this video, we're going to wrap up our building of the topology here by adding access lists on some various devices to test out to see how well you know access lists from a CCNA level. So let's just go ahead and get right into that. So let's take a look at our first objectives here. Number one, configure Telnet security using a numbered access list on R3 such that incoming Telnet sessions are only allowed if sourced from subnet A and subnet B. So if you're looking at the topology diagram, let's bring that up here. That's talking about that when the router 2 will be the only one that's allowed to actually initiate a telnet to router 3, and only if router 2 sources that telnet from either its loopback 0 or its loopback 1. So that's what we're trying to accomplish, that nobody else can initiate a telnet to router 3 unless it meets that criteria. And then we also have our credentials here that someone who telnets in should have to provide the username of admin and the password of test. Okay, so let's talk about access lists first, and then I'll ask you some questions regarding this task. So this is specifically telling us that we need to use a numbered access list. Now when it comes to numbered access lists, you have several actually different types. You've got some more advanced ones that you'll learn about at the CCNP level, like reflexive and dynamic access lists and stuff like that. But the CCNA level, they teach you primarily about two different types of numbered access lists. There's one type that's specifically designed only to let you look at the source IP address of packets. That's all it cares about. You can't match on anything else. And then there's another type of numbered access list that lets you look at pretty much almost anything you want in the layer 3 and the layer 4 header of the packet. So what are the names of those two different types of access lists? That's right, it is standard and extended access lists. So in this particular case, in order to accomplish task number 1, which one of those are we going to want to use? Now we could, which one would we want to use? That's right, we want to use a standard access list. Now, when we think about access lists for a minute, a lot of times when people think about access lists, the first thing that comes to their mind is, oh, access list means packet filtering. I would configure an access list when I want to tell my router or switch to forward or drop packets. And that's certainly one use of an access list. But I want to get your mind to stop thinking about ACLs in that way. ACLs really are just a classification tool. In other words, when you tell an access list, this is what I want to match. I want to match this source address or this destination or this TCP UDP port number. You're telling the access list what interests you, what you want to match on, but what you're not doing is the access list has no control over what's going to happen to a packet that matches the ACL. That's not the ACL's job. The ACL's job is simply to be a classification tool to report back to some feature, hey feature, you want me to look for a packet that matches this? Well, this packet that just came in, yes, it does match. Or this packet that just came in, no, it doesn't match. That's all the access list does, is report back to some other feature that it's found a matching packet. At that point, it's up to the feature that's using the ACL to decide what to do with it. Like for example, if we're talking about packet filtering, we're probably talking about the access-group feature, right? That's what you configure on your layer 3 interface, and the access group refers back to the ACL. And then the permit or the deny statement in the ACL tells the access group if it should be forwarded or filtered, forwarded or dropped. But there's lots of other features that can also use that exact same access list. For example, when you get into the world, well, for example, we already did one. We did NAT. Remember that when we did our network address translation in this lab? In that particular case, the same packet that matches the access list, if being used by a NAT feature, it's not going to be forwarded or dropped. NAT will just determine whether it should be translated or not. That's how NAT uses the ACL. When you get to the CCNP level and you get more in depth in routing, you learn that routing protocols can make extensive use of access lists. A routing protocol could use an access list to determine whether or not it's going to send a certain route to a neighbor, or whether it's going to accept a certain route from a neighbor, or whether it's going to take a bunch of routes and summarize them or not. So the access list itself, just by reading the access list, you have no idea what the result or action is going to be when something matches it. You have to know what feature is using that access list. So in this particular case, we're going to create an access list to do telnet security. What feature are we going to configure to enforce telnet security with an access list? So the access list is just a classification tool. What's the name of the feature that's going to be using this for telnet security? I'll give you a hint. It's not the access-group feature. It's something else. The feature would be the access-class feature, the access-class. So when I want to forward or filter packets on a layer 3 interface, I use the access-group. But when I'm applying an access list to a VTY line for telnet, you don't use access group, you use access class. Not sure why they made a whole different feature just for that, but they did. Now, if I was forwarding or denying packets on a layer 3 interface, and all I cared about was looking at the source address of the packet like we've got here, then actually I could use either a standard or an extended. Either access list would work. If I use an extended access list, well, an extended access list requires that you put something in the destination field, but you could just mark that with the word any, but you gotta put something there. But when you're using the access-class command, you have to use a standard access list. Access-class actually won't even really work with extended access lists. So I believe if you use an extended access list with the keyword of any in the destination, it will work, but there's really no point to that. So just from a CCNA perspective, just remember that when limiting telnet sessions with access lists, the access list needs to be a standard access list, and under your VTY line, you're going to have the access class command referring back to that access list. Now, a couple of additional things on here. You should be familiar with a couple of acronyms. The acronym ACL and the acronym ACE. What's the difference between those? When I'm talking about an ACE versus an ACL, what am I talking about? Exactly, Neil, I couldn't have said it better. That's right. Access lists are comprised of one or more lines of ACEs. So when I say access-list 101 and then I type in something, I've just created an access control entry. That one line is an access control entry. And then if I create a second line, access list 101 and something else, and then access list 101, a third thing. Now I've got 3 lines of access control entries all within one access list. The access list is 101, and it's been composed of 3 lines of individual ACEs. So as we go throughout this lab, you might see references between ACL and ACE. So at some point in this lab, it'll say, okay, you are allowed to modify ACLs, but not delete. I'm sorry. At some point in this lab, it might say, well, you can't delete the ACL, but you can modify the ACEs within that ACL. So that's why it's important to understand what the difference is between those 2 acronyms. All right, so let's go ahead and configure this access list. So we're on router 3. Let's go ahead and bring up our subnet diagram here. There we go. And I will bring up Notepad, and we'll work up our configuration on that and then apply it. Okay, so we were told that telnet sessions should only be allowed if they're coming from this network here or this network here. Everything else should be denied. So in order to accomplish that, it would probably just be easiest to create an access list with 2 ACEs. One ACE permitting subnet A as a source, and another ACE permitting subnet B as a source. And then remember, at the end of every access list is what's called the implicit deny, which means anything that did not explicitly match a permit statement is denied. So I'll just rely on the implicit deny to prevent telnet sessions from anybody else. So let's create my first access list. Now, another question. With a numbered access list, right here I have to provide a number in this spot. And the number I provide will inform the Cisco IOS which type of access list I want to use. There's a certain range of numbers for standard access lists and another range of numbers for extended access lists. In this case, because I want to use a standard access list, what's my first range of numbers I can use for that? That's right. Thank you, Diogo. It is 1 through 99. Exactly. Now, one thing they might try to get you on the certification is there's actually another range of numbers that supports standard access list. I mean, let's say you're a really large internet service provider and you've got thousands of lines of access lists and you've actually used up 1 through 99, but you still need to create more standard access lists. Does anybody know what the next range of numbers is that will give you even more? That's right, 13 to 1999. And if you have access to the command line, you can see that pretty easily. Access-list, if we do our question mark, right here, 1300 to 1999. It's called the expanded range for IP standard access lists. So you should probably memorize that range as well as the expanded range for the extended access lists. Okay, so let's go ahead and we'll just use the basic range though. We don't need to go into that expanded range. So I'll say access-list 1 permit, and then I'll use my source network, which is 8.0. And what's my wildcard mask going to be to match the subnet mask on that network? So far, I have not seen the correct answer. Anybody else? Well, our subnet mask with a /25 looks like this in binary: 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. That's a /25. So we would just invert all that. So it would be 0.0.0.127. That's going to be our wildcard mask to match a /25. And then we want to match subnet B. Permit 190, 190, 9.0. And what's the appropriate wildcard mask for that network? Well, /28 is going to look like this. That's a /28, 28 out of 32 bits. And the wildcard mask, if we invert that, is going to look like that. So it will be 0.0.0.15. That will be our wildcard mask. And then we have to apply that under our VTY lines. So line VTY, let's see here. Let's see how many VTY lines router 3 currently has. show run section line. Go to the very bottom of the config where the lines start. And he's got 5 lines, 0 through 4. So I'll have line VTY 0 through 4. And now I will say access-class 1 in. Now let's see here. Transport input all, okay. And according to this, if somebody telnets in, they should have to provide admin and test as their credentials. So that's going to require that we configure a username password statement if this router doesn't already have one. Let's take a look. Usually that's towards the top of the config. And it doesn't have one. Okay, so we'll have to provide that. So admin test capital letters. Okay? So let's just do that at the beginning. Username admin password test. Okay, so let's go ahead and put this in first. And then once I've put that in, I'm going to verify that I can telnet to router 3 from anywhere before I've installed my access lists. Okay, so let's just pick someone randomly. Let's pick switch 2. Let's go to switch 2. Show IP route OSPF, make sure he's got all of his OSPF routes. Yeah, everything looks good. Okay, so I'll just telnet to loopback 2 on router 3, which is this right here, this 3330 address. So telnet 3331. Password required but none set. Okay, so let's go back to router 3. I know why we're getting that. I want to see if you guys can figure out why we're getting that. Let's go back to, I'll give you a hint. It's in this section right here. Why did I get that message? It's because of this. Login. When you've got login configured under your VTY line, that tells the router or the switch that the password should also be configured under the VTY line. Look under the VTY to get your password, but there is no password here. I actually want to look elsewhere. I want to look at that username password statement I just configured. So what do I configure here under my VTY to tell it? Don't look at yourself, look up at the global level and find the credentials up there. That's right, I need to add login local. That's right. So let's go ahead and do that. Line VTY 064, login local. Now I should be able to get into it. Let's try it again. There we go. Admin test. And I'm in. Okay, so now let's implement the access list to restrict this. Okay, so now with that, I should no longer be able to telnet from switch 2. Yep, connection refused. If I go to router 2, oops, that's the wrong guy. Telnet 3331. So why am I getting that from router 2? I mean, after all, router 2 is connected to the approved subnets. The reason I'm getting this is because when router 2 tries to telnet to switch 3, he's not using a source IP address that's in the approved range. See, well, how do we figure that out? how would I figure out what source IP address router 2 is going to use when I'm trying to get this packet to 3331? So the way I would look at this, I'd say, well, in order to send a packet to 3331, router 2 is going to go into his IP version 4 routing table. Show IP route. And he's going to find this in there. This is his route. Oops, I should use a different color so it shows up a little bit better. Okay, so he's going to use 3330 as his route. And then he's going to say, okay, to send packets there, I would send them out fast Ethernet 0/1. So whatever IP address that he's got locally on fast Ethernet 0/1, that's what he would use as his source address. And if we look at our subnet chart right here, so he's using this right here. That means he's going to be using 190.199.27 as his source address. And that is not in the approved range. He's supposed to be using either an address here or an address here as his source in order to accomplish this. So when I initiate my telnet, I need to explicitly tell router 2 to use a source address from either subnet A, which is his loopback 0, or subnet B, which is his loopback 1. That's why it's not working right now. So let's go ahead and go back to router 2, do my telnet session, but this time do /source loopback 0. And it works. And similarly, if I do it with a source of loopback 1, that should also work. Great, so we have accomplished task number 1 in our access list. Okay, let's keep going. Task number 2, using a numbered access list, modify telnet security on router 3 such that after a network admin has successfully telnetted to this router, that admin can only initiate an outgoing telnet session to subnet Y. R1 will enforce the same telnet credentials as R3. Okay, so what we're referring to there is so we already know at this point that if the telnet starts from here as a source or here as a source, we can successfully telnet to router 3. Task number 2 is saying after we've done that and we are now telnetted into router 3, we should be able to initiate another outbound telnet session only to subnet Y. That if we're telnetted into router 3 and we try to telnet anywhere else like M or N, that should not work. That should fail. And once we get to router 1 and telnet to Y, we should have to type in the same credentials, admin and test. Okay, so my question to you, what can we do on router 3? What can we add to its current configuration so that someone who has successfully telnetted in can only successfully telnet out to subnet Y? What would you type and where would you type it? Okay, so Aziz says we should create an access list for subnet Y. Okay, so following along with that idea, what type of access list would we create? Standard or extended? That's right, we would create standard. Now some of you guys might be thinking, well, wait a second. Standard access lists only look at source IP addresses. And what we're trying to do right now is control the destination of this packet. Aren't extended access lists the only way we can control the destination? If we were using the access group feature on a layer 3 interface, for example, if we were trying to control packets that were leaving from our serial interface, yes, we would have to use an extended access list for this. But this is one of the little sort of gotchas or weird behaviors of the access class command. The access class command under your VTY line only uses standard access lists. So basically, remember that we configured right here, we configured our access class in. When you do access class in the access list, it looks at whatever you've configured for inbound packets. So when a packet's coming in, it looks at the source IP address of that packet and matches against that. Now when I do access-class out, I can still use a standard access list, but here's the weird thing. That IP address in the standard access list, which normally you think of as, oh, okay, that's a source. Well, if that access list is being used by the access class out command, that IP address is now being matched on the destination of the packet, not the source of the packet. So what we need to do now is add one more line to this. I'm just thinking, should we keep access list 1 or should we create a separate access list? We can do access list 1. We can keep it here. Add one more line, access-list 1, permit, and subnet Y is the 3.3.1 network. And then under our VTY line, access-class 1 out. So this now means if anybody ever successfully telnets into this router, and then they try to initiate an outbound telnet session, their outbound telnet session will only be successful if the destination of those packets is one of these 3 permitted subnets right here. Okay, so let's just go ahead and add in this information. Oh, no, hold on a second. Hold on a second. What I just did here actually broke one of my rules. And what I mean by that is it broke one of the objectives I had in my lab. Let's take a look at this again. Bring this right here. Can you figure it out? Let me reduce this a little bit. With what I've just configured, what did I do wrong? In other words, what restriction am I not following? Yeah, I just broke what I'm supposed to follow here in task number 1 are only allowed if sourced from subnet A and B. Because now in my inbound access list, I'm allowing inbound telnet sessions if they're sourced from subnet Y. Now anybody from subnet Y is allowed to telnet into router 3, and I'm not supposed to do that. It's only supposed to be sourced from A and B. So what do I need to fix so I can meet both objective 1 and objective 2? Yeah, I need to create a second access list. I basically need to take this line right here and put it in a different number, like access list 2 or something. Now that raises an interesting problem because I already copied and pasted this into my device. What command do I issue from privileged exec mode right here to see if I have any access lists configured and how they're configured? What show command? The command is show IP, because I'm concerned with IP version 4 access lists, access-list. Show IP access-list. So here's my dilemma. I need to get rid of this line. Can I just do this? No access-list 1 permit 333.0.000.255. If I hit the enter key, will that accomplish my objective? Will it keep these two lines and just delete the third one that I made a mistake on? No. What will happen? It'll delete the entire access list. Yeah, all lines of access list 1 will be wiped out. So I don't want to hit, right now there's only 3 lines, not a big deal, but imagine if this was hundreds of lines. I probably wouldn't want to do that. So what can I do? How do I delete just that last line while retaining the first 2? Is it even possible? Well, it is possible, but the way I have to do it is I have to treat this access list not as a numbered access list, but as if it was a named access list. See, this is one of the benefits of named access lists. As named access lists, you can delete individual ACEs, you can add an ACE in the middle of it or anywhere you want. Can't do that with a numbered access list. Nice thing is, even after I create a numbered access list like I've done right here, for editing purposes, I can treat it like a named access list. So in my particular case, I would say IP access-list. Now remember, when you say access-list without the IP, it's expected you're going to create a numbered access list. When you say IP access list, then the software assumes you're creating a named access list. So with a named access list, you then specify, is it extended? Is it standard? Well, I know the one I already created was standard. Now, normally right here, you would put your name, like Cisco, INE, whatever. In this case, because I'm modifying an existing numbered access list, I reference the number. Okay, so now at this point, what I can do is, notice how each one of these ACEs was given a sequence number, 10, 20, 30. I didn't type that in, it was just assigned that. So now what I can do is I can just delete that sequence number, no 30. End. And now when I look at my access list, that sequence number is gone. So I didn't have to delete the whole thing. I was able to delete just that one access control entry. But I had to do it as if it was a named access list. All right, so let's go ahead now and let's modify my configuration here and do this as access list 2 and then do ACL2 out. All right, so show IP access-list. Great, I've got my second unique ACL now, ACL2. Show run section line. And on my VTY line, I've got, this is controlling inbound telnet sessions. This is controlling outbound telnet sessions. All right, so let's test it out. Let's go back to router 2, because he's the only one that's allowed to telnet into this router. Telnet 3331/source loopback 0, which is subnet A. All right. And now do my telnet from here to subnet Y. Uh-oh, why am I getting this? This is because router 1, he's missing a username password statement, right? I got to do the same thing on router 1 that I did on router 3. I have to go into him, see if I look at the line here, he's just got login. I got to change that to login local and then put in a username password statement on him, just like I did in router 3. Login local, exit, username admin, password test. Now everybody should be happy. Let's try it out. All right, so initiate my telnet to router 3. And now from here, telnet to 3311. That looks better. And there we go. So we have successfully met the criteria of 1 and 2 so far. Do you have any questions before we move on to the next section of access lists? Okay, so let's continue on here. See what's next. Modify the numbered ACLU created in the previous step such that after a network admin has successfully telnetted to router 3, that admin can initiate an outgoing telnet session only to subnet N. Subnet Y is no longer allowed. Okay, so basically what we're doing here is what I already did. I sort of did a preview of this. This is testing your ability to edit an existing numbered access list without deleting the whole thing. And we just talked about that by sort of treating it as a named access list. So let's just go ahead and do that. Subnet N only, not subnet Y. Show IP access dash list. So what we want to do is in access list number 2, we want to add a new entry, a new sequence number, permitting subnet N, which is the 9.16 network. And then we want to delete sequence number 10. So IP access dash list standard, and we're referencing ACL number 2. And then we'll say, we'll create a sequence number of 5, permitting 190.190.9.16, and the appropriate subnet mask for that would be .7. And now that we've got that, we can get rid of sequence number 10. And that looks like it should work. So let's go ahead and test it out. Okay, so I can still telnet from router 2 to router 3. So now at this point, if I try telnetting to the subnet that I used to be able to reach, I should no longer be able to reach it. Yep, connections not permitted from this terminal. But if I try to telnet to the other subnet now, 9.17, that works. Okay, good. So that accomplishes task number 3. Number 4, at present, R2 may telnet directly to R1, or by first telnetting to R3 and then telnetting to R1. So just to graphically demonstrate that, what that's talking about is right now, if I start on R2, if I use a source address of A or B, I can jump over to R3, and then from R3, telnet to R1. That's one option. Or I might say, hey, you know what? If my ultimate objective is to get to R1, why not just telnet directly to R1? Because right now, R1 doesn't have any restrictions at all. There's no access lists on R1. So what this is saying now is, if we go back to our objective, it says, restrict this even further such that R2 may only telnet to R1 if the telnet first goes through R3. And it says you must utilize named access lists for this step. Okay, so what do you think? On which device would you create the named access list to accomplish this? And what restrictions would you place within that named access list? That's right, Aziz is correct. So we now need to implement the named access list on R1. And what kind of restrictions would we place in that ACL? That's right, R1's named access list should only permit incoming telnet packets if they are coming from subnets on, I wouldn't say subnets from R2, because we don't want to allow R2 to directly go to R1. R2 has to first go to R3 and then from R3. Yes, so we need to permit subnets from R3. So let's take a look at our picture again. What we need to do here is create an access list on R1. That's where our ACL should be. And that ACL should only permit packets if they were sourced from R3. You see, when R2 telnets to R3, and then from there, telnets into R1, the source IP address of those packets are going to be coming from R3. Okay, now it doesn't really say, according to our restrictions here, what source address should be permitted from R3. Okay, so let's think about this here for a second. If R2 has successfully telnetted into R3, and then from there, R3 telnets into R1, how are we going to figure out what source IP address is used in these telnet packets right here? Well, we pretty much have to do the same thing we did in the first case. We have to go into R3 and figure out, okay, well, when R3 telnets to subnet N, what is R3 going to use as a source? So we need to look at R3's routing table. We have to figure out what egress interface R3 would use to reach subnet N, because that's what he's going to use as the source IP address of his packets. Okay, so let's go into R3 and look at his routing table and see how he reaches the 9.16 network. Show IP route 190.190.9.16. And it looks like he's got two equal cost paths. He could either go out serial 000.132 or serial 000.134. Okay, since we don't know which of those particular paths he will select when initiating a telnet, our access list in router 1 is going to have to permit both of those. Okay, so show IP interface brief 132 and 134. So there are his subnets, or those are his actual IP addresses. So on R1, we'll have to do this. Access-list1 permit, we'll say host, if it's coming from this address right here. Or if it's coming from the other address, .34. So that's what R1 will have. Only permitting incoming telnet if it came from R3, and only if it's these two addresses here. We've already got the username and password statement in R1, so I don't have to do that. Actually, before I even do this, let's just verify that R2 can actually telnet directly to R1 and bypass R3, because that's what we're trying to prevent. Telnet 190.190.9.17. That's loopback 1 on R1. And yep, see, I can get in there right now, completely going around everything else. So now let's go into R1. And paste in our configuration. Okay, so at this point, R2 should no longer be able to telnet directly to that guy. Nope. But if he telnets to R3 first, and then from there, telnets, it is successful. So we have successfully met the objective in step 4. Do you have any questions? All right, we've got one more section of access list, and it's a biggie. All right, so let's look through here. Create and implement a new access list so that R2 is allowed to initiate telnet requests to R4's fast Ethernet 00 IP address. Okay, R2 is allowed to initiate telnet requests to R4's fast Ethernet 00 IP address. This telnet session, now first of all, let's just stop right here. We've just been working with the access class command. Can we use the access class command on R4 to accomplish this step, 5A? Okay, one person says yes. Does anyone disagree? Well, I would say that if we want to allow R2 to initiate requests to R4's fast Ethernet 00 and any other IP address on R4, if we didn't care if R2 is trying to get to fast Ethernet 00, fast Ethernet 01, let's go back to this. If we said, look, I just want R2 to be able to get to R4. I don't care if he goes to the IP address, here's the destination, here, or here, then yes, we could implement an access class on R4 only permitting R2 as a source. But if we were to interpret this task saying, look, R2 should only be able to go right here. If he tries to telnet to this one, or this one, he should not be allowed to do that. Then we cannot use the access class for that. Access class does not give us that level of control. So let's make that assumption. Let's assume that that's what we're trying to do, that R2 should only be allowed to telnet to this. Okay, so if we can't use the access class command on R4, how are we going to accomplish that? Well, we're going to have to use the access-group command. On some layer 3 interface somewhere, we're going to have to ensure that when R2 is initiated in telnet, it only works if it's going to here. You might think, okay, well, why don't we just implement an access-group in command right here? Because after all, if R2 is initiating a telnet, and let's say he's trying to get to this IP address, the .25 address, if we have an access-group on fast Ethernet 01 denying that, it should work, right? Do you think that would work? In other words, if I did this, if on R4 I did this. Permit host, let's just say 8.0.000.127, and it didn't say, I don't think it said where those packets are coming from. Oh yes, the telnet session will be initiated from R2's addresses in subnet C. Okay, so subnet C, that is the 9.40. And that's going to be actually the host address of 9.41. That would be R2's address in subnet C. So if we did that, and then we went to interface fast Ethernet 0/1, IP access dash group 1 in, do you think that would work? Would that accomplish this objective? Okay, let's find out. So let's think about this logically here. If router 2, if I'm going to tell router 2 to telnet to this address and use this as a source, what I'm wondering is, I don't know if that only affects the source address that he uses but does not affect his routing. In other words, if his routing table would say, okay, well, to get to .50, this is the best path. Go out fast Ethernet 00.3. Well, if I tell him to use this as a source address, I'm not sure if he's still going to use this path because this is the best path. I think it would. I think he'll choose whatever the path is in his routing table, regardless of what I tell him to use as a source address. So let's see. So let's first of all see what interface would router 2 use to get to 9.50. Show IP route 190.190.9.50. Oh, he's got some equal cost routes. Okay, so see, it gets kind of tricky here because you might be thinking, well, why don't we use this command we learned about earlier, show IP ceph exact-route, to figure out which specific interface he's going to use. The problem here is that command would work if packets are passing through R2. But this command won't work to show us what interface he's going to use if he is generating the packets. Because if his CPU is generating the packet, his CPU will be in charge of going into the routing table and figuring out which path he's going to select. He's not going to use ceph to make that decision. Ceph is only used when packets are going through the router, not when he's actually creating the packet himself. So, off the top of my head, if I'm telling him to create the packet, and he's got 3 equal cost routes, I'm not sure which of these paths his CPU will select. I'm not sure there's even a way of predicting that. So, let's see here. Well, let's just try to enforce it this way as our test. Here's what I'm going to do. I am going to shut down this interface, this interface, this interface, so the only possible way he could get there is via this. I'm still going to tell him to use .41 as his source address, but I'm going to force him to send his packets this way because that's going to be his only available route. And then once the packets come in here, we'll see if this ACL would work to deny those packets. So let's try that. Okay, so first of all, let's go ahead and apply this to router 4. And here's why I'm doing this test. This is one of these things that it's been a million years since I researched this. The question I have in my own mind is the order of processing. In other words, when a packet comes into a router's interface destined for the router itself, which happens first? Does the routing of that packet happen first, or does the enforcement of the access list happen first? If the enforcement of the access list happens first, then this packet should be dropped. If the routing of the packet happens first, then I would expect that the access list will be ignored. The router will say, oh, this packet is for me, I should process it, and then he won't even look at the ACL. So let's find out which happens first in this particular case. Okay, so we've already put that down there. Oh, interesting. Look what just happened. As soon as I put that access list in, I lost my OSPF neighbor on Fast Ethernet 0/1. Didn't want that. So what do I need to change here so that my OSPF adjacency is still functional across that interface? Well, I can't use the standard access list. Permit host. I want to, probably the best thing to do here would be to implement an extended access list saying telnet is permitted from this host. Let's think here. What would be the best way to do this? Let's bring our topology diagram back up. All right, so my objective here is if packets come in this direction, destined for this address, I want to allow it if it was sourced from right here. I want to allow OSPF and deny everything else. You know what, before we do this, maybe we should read through all the objectives in this task so we don't end up configuring something that we then later have to unconfigure to meet later objectives. So let's just see if what we're about to do will break anything else. Okay, so let's see here. R2 is allowed to initiate telnet request to R4's Fast Ethernet 00. Oops. Okay. The telnet session will be initiated from R2's subnet C. Okay, we've been talking about that. R4 is allowed to respond to these requests. Okay, it's a good thing we looked at this. Look at this. The telnet response is dropped somewhere on an intermediary device between R2 and R4. So this is telling me that the access list should not be implemented on R4. It needs to be implemented on something in between R2 and R4. Okay, good thing we didn't proceed any further with this. Okay. You may not modify the functionality of any of your existing ACLs. You must utilize TCP and UDP port numbers. Okay, so that right there tells me cannot use a standard access list. I've got to use an extended access list. Matches against any ACE within this ACL that contain the deny keyword should generate an occasional syslog verifying hit counts. How do I accomplish step number G there? 5G. That means that in my access control entry, I need to use the log keyword. The log keyword will create these syslogs. All right, so based on all of this, here's what we need to do. We now know that the access list cannot be enforced by R4 because R4 should be able to respond to that telnet session and then it gets dropped on an intermediary device. So looking at our topology diagram, that tells me that we're going to need to implement this access list on either switch 3, switch 2, or possibly both. Okay, so we already know, we just saw from the routing table on router 2 that when router 2 is trying to get to fast Ethernet 00 on R4, he's got 3 equal cost routes. He's either going to go out subinterface 00.2, subinterface 00.3, or fast Ethernet 0/1. So we know that if he goes out 00.2 or 00.3, R3 is going to be responsible for routing those packets. R3 is going to have to route those packets onto subnet E. So we would want to implement our access list on switch 3 so that he allows the telnet session to go through, and then when the response comes back, it's dropped by switch 3. Similarly, if R2 selects fast Ethernet 01, well, we know by looking at our topology diagram, our physical layer topology diagram, right here, that in reality those packets will go to switch 2 first, come in this interface, and then, that's going to be interesting because this is all one VLAN right here. So let's see here, how would they be routed? So if they go out fast Ethernet 0/1, it's going to be layer 2 switched. It's just going to be bridged, basically. It's going to go out on VLAN 5 and just be bridged across to this interface right here and go out. Okay, so let's see here. Implementing the ACL on switch 2 wouldn't have any effect because a regular access list, a layer 3 access list, is only implementable on an interface that's routing the packets. In this particular case, switch 2 is not going to be routing anything. It would just go out on VLAN 5 and be bridged across on VLAN 5. So how would we enforce this? The only way I can think of to implement this is to make sure the packets do not go out on fast Ethernet 01. If they go out on fast Ethernet 01, there's no way to accomplish this task. There's no way to ensure that the reply packets to that telnet are dropped on an intermediary device. There's no way to ensure that because it's all going to stay on VLAN 5. Now, have we been told anywhere in this task that we can do anything to prevent that? In other words, can I shut down fast Ethernet 01? If I shut that down, or if I shut down fast Ethernet 01 on the switch, okay, then I won't have to worry about this connection. Then VLAN 5 will be out of the picture, and the only way the packets can go will be this way. And then I can just implement everything here. Let's see. Have I been told not to do that? Let's see. R2 is allowed to initiate telnet session. R4, telnet is dropped somewhere. You may not modify the functionality of the existing access list, blah, 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 blah. Okay, well, let's see here. What if I go to the previous slide? Is there anything that said access lists? Okay, this is all about another session. Okay, so there's in the access list section here, there's nothing that specifically told me I can't shut down interfaces. So in order to accomplish this whole thing right here, we got a couple of choices. It's really up to you. So if you're doing this lab on your own, you've got some options here. We know that in order to accomplish this, we know that the packets have a source address of this, and we know they cannot go through subnet F. If they go through subnet F, we cannot control it. We cannot accomplish this task. So the first objective here is to make sure that when router 2 is telnetting to .50, he does not go through subnet F. Easiest thing to do would just be to shut down fast Ethernet 01. Then there's no way he can go through subnet F. If you want to be, that's what I'm going to do, just to make this easy. If you want to practice your routing skills, and Aziz has a good idea on that, we could influence routing in such a way that subnet F is available, but it's not as preferred, that it's not an equal cost route. So that would be a little bit tougher, because you could make it where subnet F is not preferred, but if you do that, then he's probably not going to use subnet F for anything. In other words, if I was to tell you, okay, I don't want you to use subnet F to reach subnet E. So let's go ahead and clean out all this stuff. Okay. If I said, okay, from router 2, when he telnets to this address right here, I want you to go this way or this way. But if he telnets to anything else, like anything over here or anything over here, then it's okay to take that path. I'm just thinking from a CCNA perspective, would you know how to do that? Well, we could probably work through that, but that's not really applicable to an access list section of our lab. So rather than going down this rat hole of manipulating OSPF costs and all that stuff, let's just make it easy and shut down this interface. All right, so that's what we're going to do. So we are going to shut this down, which will force our traffic to go this way or this way. And then we have to ask ourselves, okay, who's going to route that traffic? Because router 2 is not directly connected to subnet E. So who does he have as the next hops to get him to subnet E? All right, so let's go ahead and shut down that interface and then answer that question. Okay, so that's down. Show IP route 190.199.50. Okay, so now he has two equal cost routes, and it looks like he's using switch 3 for both of them. So in order to accomplish this access list task, I think we can do everything on switch 3. Okay, so now we know where the access list is going to be implemented. It's going to be on switch 3. So let's go back here and refresh ourselves as to what we're going to do. R2 is going to initiate a telnet request to R4's fast Ethernet 00. Check, we've got that. Telnet session will be initiated from R2's IPv4, IPv6 addresses in subnet C. One thing I didn't notice before, IPv4, IPv6. So we have to implement not only IPv4 access lists, but IPv6 access lists as well. Okay? R4 is allowed to respond. The telnet response is dropped somewhere on an intermediary device between R2 and R4. All right, so here's what we're going to do. This is going to be the source IP address. This is going to be the destination. We know that. As far as the actual path of the packets, they could go this way, in which case, and then they would be routed by SVI2, routed onto SVI4, go out, and then the reply packet would come back on SVI4. So in this particular case, SVI4 should implement our access list. So we should have an ACL inbound to drop the response of those telnets. So everything, so telnet going out will make it there, and then when the telnet response comes back, ACL inbound on SVI4 should drop it. Or if R2 chooses to use this path, it'll be routed by SVI3, once again, onto SVI4. So it looks like either way, if we do an inbound access list on interface VLAN 4, that should be able to accomplish this task. Okay. And last thing to think about, because we want to drop inbound telnet responses, if this is R2 and this is R4, what we're talking about is the telnet response going back this way. And let's think about that. In that packet, the source will be .50, destination will be .41, the protocol will be TCP. Now, in order to match on Telnet, what TCP port number will we need to match on? That's right, port 23. And will we be matching on port 23 in the TCP source port or the TCP destination port? This is the tricky part. It will be the source port. The source port, because let's think about this. When R2 initiates, when R2 initiates the telnet, the source port will be what we call an ephemeral port, some random port. We have no idea what it's going to be. The destination will be 23, but we're being told to drop it on the reply. So when this guy goes to reply back, the destination will be whatever that ephemeral port was. The source, well, he's responding from Telnet. He's responding from 23. So we want to match on a source port of 23 in the inbound direction on the reply. Okay. So here's how that's going to look. So this is going to be in switch 3. We're going to say, this is going to be pretty long here. We're going to say access-list, something in the extended range, deny TCP coming from router 4, 190.190.190.9.50, going to the host of router 2, 190.190.9.41. Okay, and here in the source is going to be EQ23. So router 4 is responding from Telnet going to router 2. And then we want to permit everything else. And on switch 3, this is going to be implemented on interface VLAN 4 IP access-group 101 in. So take a look at that for a moment and let me know if you have any questions about what we are about to implement here or why. And that's just the IPv4. I haven't even done the IPv6 yet. Any questions? Let's go ahead and implement this. First of all, let's configure R4 to even accept Telnet in the first place, because right now I don't think he has. So Aziz, to answer your question, what this access list is doing is it's saying, okay, R2 is allowed to initiate a Telnet session to R4. If R2's source is .41, that Telnet packet should be allowed to make it all the way to R4. R4 is then going to respond, but when he responds, his Telnet response is going to be dropped by an intermediary device, which in this case is switch 3 in the middle. And that is accomplishing 5D. So 5A, B, and C is permitting one direction, from 2 to 4. But 5D is saying the response is dropped. Oh, we forgot about 5G. We got to put the log keyword on that. Log. That will generate those syslog messages. Okay. All right, so first of all, let's set it up so that the Telnet is successful, because I don't think R4 has any, I don't think he's opened up for Telnet yet. He might be. Let's take a look at what R4 has. Show run section line. Okay, good. So we already set this up for Telnet and SSH. And what credentials do we have? Looks like we have INE, ISP, ARPU, admin. Okay, admin, that's probably admin test. Let's find out. Might be admin INE. Oh, it is admin test. Okay, good. So currently we can Telnet. All right, so let's go to switch 3 and implement our access list. Okay, so I haven't lost any OSPF neighbor relationships or anything. That's good, and that's because of this line right here permitting everything else. So at this point right now, R2 should still be able to ping R4. He just shouldn't be able to telnet to R4. So let's try it out. First of all, let's do our ping. Yep, we can still ping it, but we should no longer be able to telnet to it. Uh-oh, okay, something went wrong here. All right, let's figure out what went wrong here. So we got, first of all, it's probably something in the path of the packet. So let's go ahead and figure that out. Show IP route 9.50. Okay, so he's definitely going to switch 3. So let's see, how would switch 3 get there? he should be directly connected to it. Yeah, directly connected via VLAN 4. IP access group 101 in. So there it is for inbound packets on VLAN 4. Well, hold on a second. When router 4 goes to reply to those packets, is he going to go to router 3, switch 3? Let's find out. It might not have anything to do with switch 3. Maybe router 4 is somehow bypassing switch 3 in his response. Oh, hold on a second. I didn't use the correct source address. When I did that telnet from router 2, I just let him pick whatever source address he wanted. And I want to explicitly pick the source address I'm supposed to use. So let's see here. /source 190.199.41. Okay, so that's forcing him to use the source interface of subnet C. 190.190. Oh, not IP address, source. So that would be fast Ethernet 00.2. Okay, good. Whew, not working. So I think the reason it worked before, router 2 must have selected the source of fast Ethernet 00.3. That's the only way it would have worked, and that was permitted by the access list. But now that we're explicitly selecting his other subinterface, it's being blocked. And if we go to switch 3, we should see a syslog message about that. Since we put the logging, there it is. There's our syslog as a result of that log keyword. And it tells us it's denying it in the return path. Here's router 4 responding with a source port of 23, trying to go to router 2. Here's the ephemeral or random port that router 2 selected when he started the session, and it's being dropped. So let's see here. Aziz mentioned a comment. He said, should the access list be on SVI2 and SVI3 since the IP address would change? Well, we were only really concerned with, we had a couple of choices here. We know that we forced him to use this as a source address, but router 2's routing table really dictated which interface he was going to transmit on, and yes, he could have selected that to transmit out on, or he could have selected VLAN 3 to transmit out on. So we had a choice. On switch 3, we could have used inbound access lists, and if we had done that, you're right. Those inbound access lists would have been placed inbound on interface VLAN 2 or interface VLAN 3, since we didn't really know where they were going to come in. But I did know, regardless of where they were coming in, they were always going to be routed to interface VLAN 4 and then go out. And I knew that the return traffic always would come back on interface VLAN 4. Interface VLAN 4 would have to process all the return traffic. So it made more sense to me to put that inbound on interface VLAN 4. Take away all the guesswork, since I knew that interface VLAN 4 would have to respond to all that inbound traffic. Brian, you're asking, can I check that with Ceph? What exactly are you asking me to check or to verify? The path that's selected? I can't check with Ceph which path router 2 will select. I can't check that because Ceph is only used when packets are flowing through a router. So if packets, for example, were going this way through it or this way through it, or they're coming externally, then yes, Ceph is used to select which outbound path to use. But when the router's own CPU is generating the traffic, and that's what's happening right here. In this particular case, it's his CPU that's creating those packets. Ceph won't be used then. Actually, that's then process switching will be used to select the outbound path. All right, so to accomplish this, here is the config that we used on switch 3 to accomplish that task. And that brings us to the end of the access list section. Okay, so in the previous section of access lists, I focused exclusively on IP version 4, and I forgot that we were supposed to do this for IP version 6 as well. So this video here is now going to cover how we accomplished task 5 from the previous section, but doing it with IPv6. Okay, so we're back here to task 5, and to go back to the diagram, it's still the exact same thing we needed to do before. But now what we're concerned with is router 2 is going to initiate his telnet session from subinterface.2, which is going to be the IPv6 network of BB03::2 as the source, and the destination is going to be BB05::4 as the destination. So we're going to create our IPv6 access list, and it's still going to be implemented on switch 3 inbound on SVI4. Okay, so in order to accomplish this, so with IPv6 access lists, there is no such thing as numbered IPv6 access lists. And actually, to take a step back, well, so there's not IPv6 numbered, there's only IPv6 named access lists. So we have to create an IPv6 named access list, but the theory is still the same. We're still going to match on the same source and destination, still going to match on TCP port 23. So let's just go ahead and implement this. Okay, so in switch number 3, we're going to create IPv6 access-list. And now this particular case, we just give it a name. I'll just call it R2-telnet. And then enter. And IPv6 access lists are always, well, let's take a look here. Okay, they're always extended access lists. There's really no such thing as a standard IPv6 access list, which is good in this case because we do want to match on the source and destination. Okay, so we're going to say deny TCP, and in this particular case, the source is going to be the host of 2222.110.0:BB03::2. Okay, so that is R2's Fast Ethernet 00.2 interface. And then we're going to have EQ23. Actually, nope, I'm sorry, we're doing it on the reply from R4. R4's reply traffic. R4 is coming from BB05::4 EQ23. Okay, so that will deny R4's reply to the telnet going back to the host of R2. Let's change this. There. Okay, so denying telnet from R4, source port equals telnet, going to the host of R2, and then permit IPv6 any. Okay, so let's just take a look at what that ACL looks like before I actually apply it. And actually we can do show IPv6 access-list, and there it is. Deny TCP from R4 from his fast Ethernet 00. If the source port is Telnet, I put 23, but it interpreted that as Telnet, going to the host of R2, and then permit everything else. Now, the only other thing here that's different is how you apply it. With IPv4 access lists, when we went onto our interface VLAN 4, we applied it with the access group command. With IPv6, it's the traffic-filter command. And I have to give it the name, which is right here, in. So show run begin IPv6 access-list, show run interface VLAN 4. Unfortunately, I can't get it all in there. Let's see here, maybe I can do this. Show run include IPv6 access-list. That doesn't show me what I want to see. Well, I was hoping to get it all on one screen. So here's my access list up here, my named access list, and I've applied it on interface VLAN 4 right here. But I forgot. We're supposed to put the log keyword on our deny statement so we can see logs of that. Show IPv6 access-list, conf t, IPv6 access-list, R2-telnet. Copy all this. It didn't like me putting the sequence number in there. Okay, so let's just do this. Okay, that's good. So it kept it to sequence 10, and now it added the log keyword. All right, let's try it out. Okay, so let's first of all do a telnet to 2222.1100.0 BB05::4. So that's R4's fast Ethernet 00. And we'll do a source interface of the permitted interface, which is fast Ethernet 0/0.3. So this should be allowed. And it is. But now when we do the same telnet, now it should be blocked. So the telnet should make it to R2, or should make it to R4, but when R4 goes to reply via IPv6, it should be dropped on the inbound path by switch 3. And it is. It's dropped. And if we go over to switch 3, that log option shows us the syslog. And so that is the end of our IPv6 access list. Welcome back. So we are now at this point done with building our CCNA lab. We've incorporated almost virtually every technology that you would be expected to configure or monitor or troubleshoot within the CCNA. And now we're going to go into a troubleshooting section where we've got various labs that are going to come pre-built with problems, and we're going to have to solve those problems. So first of all, let's talk a little bit about an introduction to these labs and what you can expect. So just like the previous videos, all these troubleshooting labs were built on I&E's CCNA CCNP rack rental topology. So if you are going to try to recreate this, it's recommended that you use our racks to do so. Because just like everything else, if you try to recreate this on something else like your own equipment or GNS or something, you're going to run into issues primarily with like port numbers not matching up and not being the same, which will be rather difficult. You'll have to modify your troubleshooting configs, and in the process of doing that, you might see what is broken in those configs and lose the benefit of troubleshooting that problem. Okay, so at this point, I have some working configs, and if you're viewing this as a recording, you'll see in the resources or the file section of the recording, there should be a zip file there of some working configs, and there's some OSPF working configs and some EIGRP working configs. So the first several troubleshooting labs, you're going to be loading the OSPF working configs. And they're just text files. So the main idea, as a matter of fact, I'll open up one of them. You might be saying, oh, don't do that because you'll show us the problem. No, don't worry. I'll show you why it won't show you the problem. So for example, here are my files. And if I go into, for example, well, this is actually the working config. But if I go into this actually should be, now the working configs might not have everything just the way we left it. You know, some of the stuff like maybe the HSRP tracking might not be in there. Possibly the NAT might not be in there, but whatever's not in here, it's okay because it's not relevant to troubleshooting the problem anyway. So notice that these configs and the troubleshooting configs, one thing they all have in common is they start out with a whole slew of question marks, exclamation points. And I did this intentionally because my idea was, okay, when you get this, you can hit, I'm just doing it in Notepad as an example, you can hit edit, select all, edit, copy, okay, now just get rid of that, and then paste it into your router. And this will give you enough time that you can paste it into your router or your switch, and then turn your head while it's pasting in there so you don't see what's going into the device. Now clearly, you know, this isn't as elegant as our workbook solutions where we've got initial configs that you can automatically load using our, you know, control panel, but this is the next best thing. So basically, the idea is try to put these configs on there without looking at them so you don't see what the problems are. So once you've loaded the working config, the main thing to check is that you've got end-to-end reachability. So just verify that R2 has full visibility to all of the IPv4 and IPv6 routes before proceeding on to loading a troubleshooting config. Avert your eyes during the troubleshooting. Okay, and one other thing I'll mention about this. These labs they're not successive. And what I mean by that is, you know, once let's say you start with troubleshooting lab number 1 and you find the problem, you fix it, and then you want to move on to the next one. So you can go to any of these labs in any order, troubleshooting 1, 7, 6, 2, but here's the key. Before you start, ideally what you would do is you would write, erase, and reload all the devices, and then load the working config onto all the devices, and then load the troubleshooting configs onto all devices. Now I realize that'll probably take a good 15 minutes or so up front just to get it to that state. If you're a little impatient, you can probably leave off the write, erase, and reload, but definitely before you do any of the troubleshooting labs, go back to the working configs, load the working config, and then load the troubleshooting configs. Because if you, for example, if I finish troubleshooting lab number 1 and I think I fixed it, there might still be some access lists or something in place there which could screw up troubleshooting lab number 4 or number 9 or something. And the working configs will get it right back to the beginning state so you can jump around to any troubleshooting lab that you want. So this is CCNA troubleshooting lab number 1. Once again, if you're following along with this or if you're doing this on I&E's CCNA racks, one thing I would definitely recommend is before you do this first lab, write erase all of your devices and reload them. Set them all back to factory default, then load the working configs and move on from there. You won't have to do that after this first lab, but definitely for the first lab, if you already built up the monster lab that I call it before this, you want to clean all that stuff out and then put the OSPF working configs onto this. Now as we move forward, for example, when you're done with this and we move into lab 2 or lab 3 or something, just as an example, if you finish lab number 1 and you realize that the only device you actually changed in any way, let's just pick one at random here. Let's say it was router 1. Let's say router 1 was the one that you actually fixed. That's the one that had the problem on it. Well, now when you move into the next lab, like lab 2 or lab 3, you don't have to load the OSPF working config on all 7 devices because you never touched the other 6 of them. Just load the working config on the one that you fixed in the last lab, the one that you changed, and that'll save you a lot of time as well. So here's our problem description. R2 cannot ping the loopback 2 of R3. Let's verify that that actually is true. So here I am on R2, loopback 2 of R3, which is 3331. Okay, yes, I cannot ping it. It's not working. Lab restrictions. No changes to the physical layer topology are allowed. The reason why it says that is because in some of these labs, interfaces might be administratively down, and that is intentional. Or maybe interfaces are up that you did not expect. That is intentional. So you are not allowed to shut down or do a no-shut on an interface unless the lab actually tells you to do that. In this case, we're not being told we can do that. Any existing access lists may not be deleted. However, individual access control entries may be deleted or changed. IP access group commands may not be modified or removed from an interface. You must ensure that the finished working lab adheres to the original lab specifications. That's sort of like a catch-all phrase saying, look, you can't just decide, oh, to fix this, I'm just going to wipe out OSPF and configure RIP instead. Or I'm going to change my IP addressing plan. Big dramatic changes like that as simple workarounds, you can't do. Basically just think to yourself, okay, if this is a live production environment, is the change I'm thinking of doing something that would be impacting a lot of people negatively, possibly? Then if that's the case, don't do it. Okay, so we know that we can't ping the loopback of router 3. So the way I'm going to go through these labs is when it comes to troubleshooting, there's a lot of different ways to troubleshoot something. There's no one correct way. Just like there's a lot of incorrect ways to troubleshooting. For example, if I can't ping, if I all of a sudden throw up my hands in despair and say, oh, the sky is falling, the sky is falling. Well, yeah, that's probably the wrong way to troubleshoot it. Or if I go to my manager and say, I think the network is dead, also probably the wrong way to troubleshoot it. But similarly, there's more than one right way to troubleshoot it. So I'm just going to go through this using the thought process I would use, which may be different than the way you used, but hopefully you can gain some insight from it. Okay, so let's expand this a little bit. So we already know that I can't ping. So the very first thing I would check would be to see if I even have a route to this. I would check my layer 3 routing table. Show IP route 3331. Okay, no network in table. Now I know that, I'm coming to this topology and I know that I'm supposed to have a route and it's supposed to be OSPF. This is working, this is based on the monster config we just finished. Everything was functional via OSPF. So now I have to wonder, okay, where are my OSPF routes? Do I have any other ones? Any other OSPF routes? No. Well, I got a couple here. I've only got 2 OSPF routes, but where are all the other ones? Okay, the next thing I would look at is I'd say, okay, do I have all the OSPF neighbors I'm supposed to have? Am I communicating with who I'm supposed to be communicating with? Show IP OSPF neighbor. So looking at this, So it says my neighbor, I do have two neighbors in the full state. That's good. I have a neighbor on 00.3 and 00.2. Okay, well, let's just go down that trail. Now, I remember from the previous lab that I should have had also a neighbor on Fast Ethernet 01, and I don't see that. But that's not necessarily critical to be able to ping here. I mean, at a very minimum, one neighbor should be giving me the route. Now, yeah, I probably want to troubleshoot at some point why I'm missing the third neighbor, but at least one of these guys should have sent me the route to that network. So let me troubleshoot and figure out what's going on with them. Okay, so let's now go to, let's see here, dot 46 and dot 42. That is switch 3. So let me jump over to switch 3. And first of all, let me see, can I even ping? Well, let's just jump over to switch 3. Same thing, show IP route 3331. Network not in table. Okay, who does he have as OSPF neighbors? Okay, so he's got neighbors on VLANs 1, 2, 3, and 6. So if I look at my topology diagram right here, switch 3, 1, 2, 3, and 6. So he's got a neighbor right here. So there's a neighbor on that interface. Neighbor on VLAN 2. So he's got a neighbor right there. He's got a neighbor right here, VLAN 3. And he's got a neighbor right here, VLAN 6. But we've been trying to ping this network right here. And looking at our topology diagram, the only one that could possibly advertise that network to him is router 4. And we don't have router 4 as a neighbor. Okay, what about switch 2? Does switch 2 have router 4 as a neighbor? Let's find out. Okay, so once again, switch 2 does not have router 4 as a neighbor. So router 4 is cut off from our topology. That's why we haven't learned of any routes to that loopback. So now we've isolated our problem here. We know, looking at our topology diagram, we have to troubleshoot why there's no neighbor relationship with router 4. So we could take this from one of two standpoints. We could either troubleshoot why switch 2 doesn't have a neighbor relationship, and or why switch 3 doesn't have a neighbor relationship. Okay, so let's start with switch 2. Just randomly, let's just pick him and figure out why he does not have an OSPF neighbor relationship with router 4. So switch 2. So if I don't have a neighbor relationship, the next thing that would come to my mind is, okay, well, in order for a neighbor relationship to even form in the first place, OSPF would have to be active on this interface, right? OSPF would have to be active on SVI 5 because router 4 is also in VLAN 5. At least I assume it is. It's supposed to be. So let's see if OSPF is indeed active on interface VLAN 5. Show IP OSPF interface brief. Okay. It is. It is active. All right, and it says, oh, it looks like I used to have a neighbor. And the neighbor's down. Okay, but at least I know that interface VLAN 5 is covered by an OSPF statement. It's not a missing or incorrect network statement of some kind. All right, so further troubleshooting. Let's go ahead and take a look at interface VLAN 5 and the configuration and see if we can spot anything that might be in there that prevented our neighbor relationship. Show run interface VLAN 5. Okay, and at this point, what I'm going to do is I'm going to open up a second connection so I can compare router 4 and who his neighbors are at the same time. Okay, So interface VLAN 5. So looking at our topology diagram once again, what I need to focus in on router 4 is if I'm concerned with the neighbor relationship between switch 2 and router 4, then I'm talking about this right here. So I want to look at his fast Ethernet 01. Show run interface fast Ethernet 01. Okay, let's just compare some basic stuff. Are they in the same subnet? Yes, they are in the same subnet. Okay, they're using authentication. Is it the same kind of authentication? Yes, it is. Are they using the same password? Yes, they are. Is either one of these interfaces shut down? No, it's not. Okay, so there's nothing at the interface level that would cause me to not have a neighbor relationship. Okay, so the next thing I would check, so at layer 3, let's just check router 4 and let's look at his OSPF process. Let's do show IP OSPF interface brief because we did not check yet on router 4 to see if OSPF was working on his fast Ethernet 0/1. Let's expand this just a little bit so it's a little bit clearer. Okay, it is fast Ethernet 0/1. It is covered on there. It says it's in area 0 over here. VLAN 5 was in area 0, so they're in the same area. Okay, no problem there. Let's look at our running config now and go down to our OSPF process and see if we can spot anything that would explain the lack of relationship between these two. All right, so there is our process on switch 2, show run section OSPF. Okay, and let's just line these up here. Okay, so here we go. So we already know that we've got the correct network statements because otherwise it wouldn't show up in the interface in the first place. So I don't see any other funky, weird commands here in the OSPF process that would prevent them from talking. Similarly, if I go back to my interface, show run interface fast Ethernet 0/1. Oh, wrong guy. Show run interface VLAN 5. Okay, I don't see any access lists or anything here preventing them talking. On router 4 side, show run interface fast Ethernet 0/1. Don't see any access lists here preventing them from talking. So from a layer 3 perspective, everything looks great. I don't see any problems here with the OSPF configuration or with the IP configuration. So now at this point, I would have to check off layer 3 and I would decide to start moving down the OSI stack. So let's move down to layer 2 now and check that out. So while we're on router 4 here, let's just take a look at his interface. Show interface fast Ethernet 0/1. Let's try that again. Okay, it says it's up. Line protocol is up. Looks good. Okay, we got full duplex, 100 megabits per second. All right, now let's go ahead and from a layer 2 perspective, there's really not much else we can check on router 4. So now let's check on the switch, his layer 2. So layer 2 would mean checking the VLANs and the VLAN to port assignments. So it's supposed to be in VLAN 5, so we got interface VLAN 5. So let's check now on switch 2 what kind of VLANs we have. Let's do that again so it's a little bit easier to see. Do you see something missing? Where's VLAN 5? If we go back to our diagram right here, actually let's go back to this diagram. If you recall, this whole section right here and all these interfaces are supposed to be in the broadcast domain known as VLAN 5. And we don't see VLAN 5 here. VLAN 5 does not exist in my output. Let's check the configuration of the actual physical port that's connecting switch 2 to router 4. And checking my configuration here, that is port 0/4. Show run interface fast Ethernet 0/4. Well, I think we've identified at least one problem. The interface is correctly configured to be in VLAN 5. It is an access port, but VLAN 5 does not actually exist. That's going to be a problem. Furthermore, if I do show interface fast Ethernet 0/4 switch port, look at this. Access mode VLAN inactive. So this port is in a VLAN that does not exist. And when that happens, the port might as well not even be there. It's not functional at all. All right, so let's see if we can fix this. The port's already in the correct VLAN. The VLAN doesn't exist. So all we need to do at this point is create the VLAN. And let's see if that solves all of our problems. Ah, look at that. Now I have an OSPF neighbor relationship. Ah, I just got a neighbor relationship with router 2, who is the guy I was trying to ping from in the first place, and router 4. So now can I do my ping from router 2 again? Does router 2 now have the route? Show IP route 3331. Look at that. He's got a route. And the ping is successful. Now, in this particular example, we started out by realizing that we had problems on both switch 3 and switch 2. Neither one of them had an OSPF relationship with router 4. And we just figured out the problem on switch 2. Before we leave this troubleshooting lab, you know, we could have easily just started with switch 3. It was just random that we decided to start with switch 2. But let's say we had started with switch 3 in the first place. Let's see what kind of problem he has so we can fix that. Now, what I would do is, if I've already discovered one problem on one device, I'd say, okay, let me just see if that same problem exists on the other device. Because if it does, that'll save me a lot of time in troubleshooting. You know, why pretend like this didn't happen? Let's learn from this and move on to the other device and see if we can see the same problem there. Okay, so from our, if you remember from when we built this lab, originally, and we can see here, this connection was in VLAN 4. So since VLAN 5 didn't exist in switch 2, is there a possibility that VLAN 4 does not exist in switch 3? Wouldn't that be sneaky? Well, let's find out. Show VLAN. VLAN 4 does exist, but wait a second. I think I do see a problem. Notice on switch 3, VLAN 4 exists, but shouldn't there be a port right here? Remember, when a port is an access port in a particular VLAN, it should show up on the right. Like all these ports right now are access ports, switch port mode access, and they're all in VLAN 1. Well, going back to our original diagram, this one, this port right here, port 0/4, was configured as an access port. At least it was back when we built this lab, in VLAN 4. And yet it's not showing up in the output of this. So let's go ahead and take a look at the configuration of that port. Show run interface fast Ethernet 0/4. Aha. Same problem, but in reverse. This time the correct VLAN existed, but the port is in the wrong VLAN. interface fast Ethernet 0/4, switch port access VLAN 4. And there we go. Just got my OSPF neighbor relationship up. Show IP route 3331. He now has an OSPF route to that. And so now if we go back to R2, R2 should now have 2 routes to get to 3331. This is clearly the best route. Show IP OSPF database. Summary. And we're looking for a summary LSA. Actually, he only would have received a single summary LSA. If we go back to our diagram here, it would have been router 4, who when he learned about network X, router 4 would have sent a type 3 summary LSA to his neighbors. And so in router 2's database, he's only going to have a single type 3 summary LSA, the one type 3 summary LSA that was generated from router 4. And then it's up to him to pick whichever path is the best path. So it's okay that he only has one route in his routing table. So in this particular lab, switch 2 and switch 3 had incorrect VLAN to port assignments. On switch 2, his port was in the right VLAN, but the VLAN itself didn't exist. So we had to create it again. On switch 3, the correct VLAN, VLAN 4, did exist, but the port leading to router 4 was not in that VLAN. It was in VLAN 44. That was a mistake. There is no VLAN 44 in this topology. That was incorrect. So that is the solution to this lab. And now we're going to move into troubleshooting lab number 2. If you haven't already done so, please load the OSPF working config back onto the device or devices that you detected the problem in the last troubleshooting lab that you did, and then proceed to load the troubleshooting lab 2 configs on all 7 devices. Same general problem description. R2 cannot ping the loopback 2 of R3. Let's verify that is still a problem. And yes, we cannot ping it. Lab restrictions. All the lab restrictions here are the same as in troubleshooting lab number 1 in the event that you've already done that one. Otherwise, just pause the recording for a moment and read through these before proceeding to troubleshoot. Okay, so let's go through this and try to figure out the problem. So I would start the same way. I would start by checking to see if I have a route to the destination I'm trying to reach. And I do. So I have a route. And this route was learned via fast Ethernet 0/1 from 4444. Okay, then let's go to router 4. He should also have a route since he had something to send to me, but let's just check. Show IP route 3331. Okay, and it looks like he has a static route. And his static route is pointing at 9.34 as the next hop. So if we look at our topology diagram just to see where that is, 9.34, if you've been following along in the Monster Lab that we built, is the interface on router 3's serial 000.134. Okay, so it looks like from router 2, if we're going to ping 3331, router 2 does have an OSPF route that gets those packets to router 4, and then router 4 has a static route which gets those packets to router 3. So apparently the problem is not that the ping is not